Hi, everyone. My name is Sam Lounder. I'm a PhD candidate studying under Professor AIChE at Tufts University. And today I'll be talking about a new membrane cross-linking approach that has been recently developed by our group. This approach allows us to tune the effective pore size of self-assembled zwitterionic copolymer membranes all the way down to less than 1 nanometer in diameter. This grants these membranes with excellent ion selectivity as well as fouling resistance. Membranes are an efficient technology for the removal of salt from water. This is important for a host of different applications, such as the production of potable drinking water through the desalination of saline water sources, such as seawater or brackish water, and also for the removal of more troublesome ions, such as toxic metals and fluoride, and then also scaling-prone divalent ions like sulfate and calcium. Polyamide thin film composites are the current leading membrane technology for these various applications. These membranes have high water flux and do succeed in filtering salts from water. However, they have several key drawbacks as well. One of these is that the membranes have challenges with achieving targeted ion selectivity. So for example, it's difficult to remove selectively sulfate or fluoride while freely passing chloride. Polyamides are also prone to membrane fouling, which is the absorption of feed components onto the membrane surface. This can have significant effects on the membrane performance and also lead to a reduced membrane lifetime. The aim of our research group in Professor Asatakan's lab is to develop new membrane materials that can address key issues such as this, such as ion selectivity and fouling resistance, by virtue of their design. One such new material that's attracted a lot of interest are self-assembling copolymers, which are copolymers that are able to spontaneously form ordered nanostructures. In comparison to standard membranes that do not have nanostructure, self-assembled copolymer membranes have ideal features, such as a uniform pore size, controlled pore functionality. Furthermore, due to the spontaneity of the self-assembling process, these membranes can be fabricated using scalable methods. Most self-assembled copolymer membranes made to date have effective pore sizes that are in the range of 5 nanometers or greater. And so it's been difficult to achieve appreciable ion selectivity using these membranes. The self-assembling copolymers that are the subject of my own research are random zwitterionic amphiphilic copolymers, or RZACs. These are random copolymers comprised of zwitterionic and hydrophobic building blocks, all arranged in a random or near random fashion along the copolymer backbone. A zwitterion is defined as a molecule with an equal number of positive and negative charges. This grants zwitterions with extreme hydrophilicity and fouling resistance, and also grants them with interesting self-assembling properties as well. Previous work from our group has shown that RZACs are able to self-assemble to form a bicontinuous network featuring zwitterionic nanochannels surrounded by the hydrophobic phase of the copolymer. What we do is we coat RZACs onto commercial ultrafiltration membranes, and then water and small solutes, including ions, are able to permeate through these zwitterionic nanochannels. These membranes, due to the hydrophilicity of the zwitterionic domain, have exceptional fouling resistance. However, the pore size is too large right now to filter ions. And so that's the aim of my research is in this current presentation is to confer ion selectivity to these RZAC membranes while maintaining fouling resistance. To achieve this goal, we developed cross-linkable RZAC membranes. These are RZACs that have a cross-linkable hydrophobic group, these allylic CC double bonds. When these membranes self-assemble, they form the same bicontinuous network, but now the hydrophobic domain possesses this allylic functionality, which allows for it to be cross-linked. And this cross-linking, as I'll show throughout this presentation, allows us to tune the membrane selectivity. To prepare these membranes, we simply coat a polymer solution onto a commercial ultrafiltration membrane and allow this solvent to evaporate. And this is overall a very scalable fabrication technique that is compatible with roll-to-roll manufacturing. And the SEM cross-sectional images show that this approach affords a membrane selective layer approximately 500 nanometers in thickness. To cross-link these membranes, we first equilibrate the membrane with a solution of alcohol and photoinitiator. We then shine UV light and this leads to the photopolymerization of the hydrophobic domain, thereby cross-linking the hydrophobic domain. This was confirmed by ATR FTIR measurements of copolymer films before and after cross-linking. We observed a decrease in the characteristic allopy, which confirms that we were able to cross-link a significant portion of these groups. So you might be asking, why does this affect selectivity to cross-link the hydrophobic domain? Well, what we observed before and after cross-linking was a decrease in water uptake, and this reflects a decrease in the effective pore size. What we're observing is that water is not able to expand the hydrophobic domain as extensively after cross-linking, and so the zwitterionic nanochannels are now unable to attain a larger size. To test the effect of this on membrane performance, we would test neat uncrossed membranes, and then we would cross-link, and then test them again afterwards. We first looked at the effect on membrane permeance. What we see is a decrease in the membrane permeance using these various cross-linking conditions that we explored. We tried different cross-linking times and photoinitiators, and the general observation was that more intense cross-linking conditions led to a greater decrease in the membrane permeance. And so this, to us, implies that the decrease in pore size is corresponded to the overall degree of cross-linking. So now on to how this tunes the membrane selectivity. We examined first the change in the rejection and the selectivity enhancement of sucrose, which is a neutral molecule approximately 1 nanometer in size, slightly less. The selectivity enhancement is defined as the concentration of the permeate for a given solute, in this case sucrose, that's exiting the initial membrane, which is uncross-linked, divided by that of the cross-linked membrane. So for example, selectivity enhancement of 10 means that the permeate is 10 times more dilute upon cross-linking. And this would be a rejection change of, changing from a rejection of 90% up to 99%. And for sucrose, we see both the increase in rejection and this exponential increase in selectivity enhancement as a function of the decreased membrane permeance. And so this shows that we're able to really dial in the effect of membrane pore size and control selectivity in a predictable way. We observed this for neutral sucrose, but we also saw this for sodium sulfate and magnesium chloride, which are salts containing scaling-prone divalent ions. For sodium chloride, however, we did not see such a drastic change in its rejection. And so this suggests that this approach is very well suited for the development of membranes for water softening, since clearly we are able to achieve high rejections of these divalents while maintaining a low rejection of sodium chloride, which is ideal for these applications. Crucially, we wanted to test the fouling resistance of these membranes upon cross-linking. We tested the fouling resistance using both proteins and organic foulants, and we observed minimal fouling, minimum flux decline throughout the fouling experiment. And then we observed complete flux recovery upon a simple DI water rinse. This shows that these membranes are completely resistant to irreversible fouling, and shows that our cross-linking approach does not sacrifice the fouling resistance. We next wanted to study the selectivity of the most highly cross-linked membranes. To do this, we started by filtering neutral solutes of varying Stokes diameter, which we used to characterize the size. We observed precise size-based selectivity, which is a lower rejection of the smaller solutes. And we also determined that the effective nanochannel size was less than 1 nanometer, since the retention of sucrose, which is 0.94 nanometers, was 99.7%. We next wanted to characterize the salt selectivity of these highly cross-linked membranes. To do this, we filtered 20 millimolar solutions of sodium sulfate, magnesium chloride, and sodium chloride. These were carried out at 250 psi operating pressure, which amounted to between 6 and 7 LMH operating flux. We observed a very high retention, about 99.4% of the salts containing sulfate, which shows that these membranes are able to reject sulfate. And meanwhile, we still observe a low retention of sodium chloride. While these results are promising, for these membranes to be useful in a realistic application, they would need to be able to maintain the selectivity with complex mixtures. To test this, we filtered artificial seawater, which is a highly saline and mixed feedstock. And again, we observed these nearly identical rejections to the case of the single salt solutions. We maintain a high rejection of sodium sulfate, a moderately high, like above 90% rejection of magnesium, and then a low retention of these monovalents. And we benchmark this performance using the NF90, which is a premier nanofiltration membrane. And we observe superior selectivity in terms of sulfate removal. We compared the selectivity to other existing membranes, namely commercial polyamide thin film composites, as well as polyamide thin film nanocomposites. And then down below in this gold box shown in the figure with the star symbols is the sulfate chloride selectivity for other premier self-assembled copolymer membranes. And so you can see that this approach not only enables excellent selectivity in comparison to the state-of-the-art technologies, but it also far surpasses that of previous self-assembled copolymer membranes. So I can't get into the details to a great extent for the source of the selectivity, but we suspect that the reason for this excellent chloride sulfate selectivity was due to selective interactions occurring within the nanochannel. It's known that sulfobadiene, which is the zwitterine lining the nanopore wall of these membranes, has strong and selective interactions with with anions. It prefers to interact with weakly hydrated anions like perchlorate and iodide, more so than strongly hydrated ones such as fluoride and sulfate. So we can't dive too deep into these results, but I'm showing here the rejection of different sodium salts with varying anion species, and we're observing a lower retention corresponding to these salts which possess anions that interact more favorably with the zwitterionic groups. So it seems that favorable anion interactions result in a lower rejection. If you're interested in understanding the mechanisms behind the selectivity, I encourage you to view my PI's presentation where we dive deeply into the mechanisms underlying this transport. But for practical purposes, we're interested in this chloride-fluoride selectivity that we're observing for these, again, 20 millimolar single salt solutions. This is an important separation for the removal of fluoride from drinking water. You want to remove fluoride, but not excessively remove chloride, since people would prefer to drink water with some salt. And so this would necessitate an additional remineralization step if you remove too much of the sodium and chloride. To test if these membranes could perform these selective separations, again using complex mixtures, we filtered equimolar solutions of sodium chloride and sodium fluoride. And again, we observed that these membranes are able to maintain the selectivity in the mixed mode versus the single salt mode. And again, in comparison to state-of-the-art membrane technologies, namely commercial polyamides and layer-by-layer membranes, we're again observing excellent selectivity. And this is due to the selective interactions occurring within the nanochannel, coupled with the effects of confinement due to the small sub-nanometer pore size. So that's the end of this talk. I would like to conclude by saying that in this work, we hope to have shown cross-linkable AIChE membranes present a new platform for tuning the selectivity of fouling-resistant membranes and enabling the pore size reductions all the way down to less than 1 nanometer. We also saw that these membranes maintain their fouling resistance and that they have exceptional chloride sulfate and chloride fluoride selectivity. And this is again due to the selective interactions occurring within the nanochannel, as well as the really small pore sizes that we were able to access by this approach. So I'd like to thank, first and foremost, my PI, Professor Astataken, for all of her help and mentorship in this project. And I also would like to thank my lab mates for their helpful discussions and support in general. And I would like to thank the NSF funding, which allows me to work on these cool membranes. And I would also like to throw out a thanks to the Tufts Institute of the Environment, who has funded much of this work involving the chloride-fluoride selectivity through the 2020 TIE Fellowship. And I also would like to thank Zwitterco, a startup that's looking to commercialize AIChE membranes and also some of this work for their helpful discussions for the potential of scale-up. And especially I'd like to thank Chris Drover, the CTO. So, and I want to thank you, my audience, for your time and attention. Thank you.